Hello. In this video, we'll talk about the simplified or how to simplify radicals. Keep in mind, radicals is the roots. For example, square root is an example or is a form of a radical. So when we speak of radicals, we're really referring to roots. Common, you have what is called a square root. Okay, square root is just the form, is one example of a radical or a root. So we have square root, and the square root, meaning the index is 2. And if you remember, the index is what goes there, okay, where that red dot is. For square root, it's understood that the index is 2, okay. We also have cube root, and here the index is 3, and then we have fourth root and so on. So we can also refer to these as radical, okay? So this here is what we call our radical, okay? So what we want to do is, how do we simplify radicals? We know how to simplify radicals when the radicand is a perfect square or a perfect cube. So, for example, if I ask you to simplify, okay, the root of 16. Now, because the index here is 2, what number when you multiply it by itself twice? Since the index is 2, hence the word square root, okay, what number, and must be a single number when multiplied by itself, okay, gives 16. And that number will be 4. If you take 4, okay, if you take 4 and you multiply it by itself, you get 16. So the square root of 16 is 4. Hence, we say, okay, hence, this means 16 is a perfect square, because we're able to find a number when multiplied by itself that gives 16. For example, 25 will also be a perfect square. Okay. Simplify the square root of 25. Because 5 times 5 is equal to 25, then we say 25 is a perfect square. But if we have something such as 12, okay, there is no number when multiplied by itself that gives 12. Okay, so if we ask to simplify the square root of 12, note 12 is not a perfect square, these are the types of radicals we want to simplify. We're looking to simplify radicals where the radicand is not perfect square, possibly, sometimes they can. And also we look at simplifying radicals where the radicand can be a variable. Okay, so that's what we want to look at. Before we get into that, there is a property or a few property. There's a few properties that I would like to go over. Let's call this property for radicals. And that property, okay, will help you to understand how we get some of, or what we do. If we have the nth root of a times b, this is the same as if we write the nth root of a times the nth root of b. Okay. Now, keep in mind how we get this, right? Or if we have ab raised to the 1 over n power, this is the same as a raised to the 1 over n times b raised to the 1 over n. Okay? Because remember, all radicals can be written as some fractional power. Okay? And the same, so let's call this property 1. And then property number 2 that we'll look at, if we have the nth root of a divided by b, this is the same as the nth root of a divided by the nth root of, let's write that, the nth root of b. And then please keep in mind, obviously here, because b is in the denominator, b cannot be equal to 0, right? Because we have some fraction. So, and we just want to remember of a reminder of perfect squares. So perfect squares will be 0. Why? Because 0 times 0 is equal to 0. 1, why? Question mark. Because 1 times 1 is equal to 1. 2 is not, 3 is not, 4 is a perfect square. Why? Because 2 times 2 is equal to 4. Right? Once you can find a number when multiply, and this list goes on and on and on. Okay, this list doesn't end. Okay. Now, perfect squares will help you. Okay, because if I ask you to simplify, let's say, so this is an example, the square root of 50. Okay. Well, 50, so you want to make sure you notice 50 is not a perfect square. Okay, 50 is not a perfect square, meaning there is no number when multiplied by itself gives 50. Yeah. So what are the factors of 50? Okay. We want to look and see what two numbers, okay? So we're looking for find two numbers, find two numbers when multiplied gives 50. But one of them must be a perfect square. Okay? Very important, very, very important. But one of them must be a perfect square. So let's look at what I'm saying here, right? We have the square root of 50. Well, the square root of 50, we can have the square root of 2 times 25. That gives 50. We can have the square root of 10 times 5. That is 50. Or we can have the square root of 1 times 50. Or we can have the square root of, and this list goes on and on, right? This list can go on and on and on. Okay. So let's just say, let's look at the three of them that we have here. Okay. So one here, one here, one here. Now, as I said, one of the numbers here, one of the numbers, either this number or this number here, okay, must be a perfect square. Okay. One of them has to be a perfect square, meaning you know the square root. You know the square root of one of these numbers. Okay. So either you know the square root of 2, which you don't. Okay. Either you know the square root of 2, which you don't. 2 is not a perfect square. Or you know the square root of 25. But 25 is a perfect square. Okay. And if you didn't choose that, look, 10 is not a perfect square, meaning you don't know the square root of 10. 5 is not a perfect square. You don't know the square root of 5. 1 is a perfect square, but you still can simplify it 50. Okay. So usually 1 times a number is not an option. Okay? So this is the one we choose. Okay. So now we have that the square root of 50 is the same as the square root of 25 times 2. And using the property that we have up here, property number 1, yeah, if we have this, we can break the square roots up. So now we can go back here and say, well, listen, this is the same as the square root of 25 times the square root of 2. Yeah, same. And we know that this is a perfect square. The square root of 25 is 5. The square root of 2 we don't know, so that just becomes square root of 2. Now it's very important that when you think you're finished, always look and see, can you simplify that again? Are there two numbers that multiply to give 2 where one of them is a perfect square? Because sometimes you will think that you are finished and you're not. And I'll show you examples of these. So here, the square root, so your answer, the square root of 50 can be simplified as 5 root 2. And this is what we mean by simplifying radicals. Let's look at another example. So let's look at simplify square root of 12. Okay. Square root of 12. Now, 12 is not a perfect square, okay? So note 12 is not a perfect square. Meaning you cannot find a number when you multiply that number by itself, you will get 50, okay? So what are the factors of 50? Well, sorry, the factors of 12, sorry. So we have 2 times 6, okay? Or we have 3 times 4, and 1 times 12. 1 times 12, we don't really take that because we don't usually use 1 times 12, okay? This is an option that you should not really take 1 times 12 for any simplification. But if you notice, here 4 is a perfect square, okay? In the other scenario, none of these numbers here are perfect square. So what we'll do, we'll take, okay, the square root of 12 is the same as the square root of 3 times 4. And we know we can rewrite this, and I always like to write the one perfect square for square root of 4 times square root of 3, okay? And this is just my style. I always tend to write the root that is the perfect square first, okay? The reason I do that is because I know the square root of 4 is 2, and the square root of 3 cannot be simplified, so we just write square root of 3. So we say the square root of 12 is the same as the square root of 2, the root 2 root 3. And please make sure when you make your radical, right, that the line at the top covers everything or covers the radicand, okay? Very important. And this is our final answer here. Let's look at another example. Simplify square root of 72. Okay? Square root of 72. So 72, you should observe, note, 72 is not a perfect square. And once again, we say this because there is number when multiplied by itself gives 72. Okay. Now, if we go through our list as we're doing, and we only do this sort of like scrap work, once you get the hang of it, you don't need to go through this list. So here we have 2 times 36. Okay. 2 times 36. Or we have many more square root. We have 3 times 24. Okay. We have, so all of these are factors, and the list probably goes on 9 times 8. Okay. We have 6 times 12 and so on. So I'm only listing a few of them so you can see. Now, if you notice here, we have 2 choices to use. Okay. If we notice here, we have 2 choices. 36 is a perfect square, so we could use this one here. But then we also have a square here, 9. But notice that if you use this one here, you will have additional work to do. Okay? Your problem becomes a little bit longer. You can use either or. So let's see if we use if we use the first one. And then I'll also show you, right? So I'll do this problem twice using different, and you will see the difference. So the square root of 72 is the same as if we write the square root of 2 times 36, okay? And then this here, you could write it, the square root of 36 times the square root of 2, okay? And the square root of 36, you know, is 6, so we end up with 6 root 2. So here is our final answer. Now, if you use this scenario, the square root of 72 is the same as the square root of 9 times 8. And here we know, okay, this becomes the square root of 9 times the square root of 8. The square root of 9 we know is 3, so here we have 3 root 8. And this is the reason I said earlier, always look at this here to see if you can simplify. Well, 8 can be simplified. 8 is the same as 4 times 2. And then once again, if we have the square 3 times the square root of 4 times 2, you could rewrite this as the square root of 4 times the square root of 2. And this, the square root of 4 is 2. So we have 3 times 2 square root of 2. And 3 times 2 becomes 6 root 2. You will get the same answer, but the concern is that you may stop here. Okay, you may tend to stop here. Do not stop here. Don't stop. Always check when you think you're finished. Okay, always check. So you just have to be careful. Okay, just have to be a little bit careful. And once you find the factors, just check your answer at the end, because we know that 2 cannot be simplified, only 1 times 2. And we don't take the factor when it's 1. Now, what happens when we have letters? Okay, suppose I ask you to simplify the square root of x to the 6th. Okay, now remember, we can, okay, remember, we can write radicals using exponents. Okay. So we can say that the square root of x to the 6, or that is the same as x to the 6. Let me use a color so you will see this better. X to the 6, and then in exponent form, that's the same as 1/2, right? Because the index here is a 2, okay? That index is a 2. So that's where I'm getting the 1/2 from. Now, if you remember, when we have an exponent raised to an exponent, all we do is multiply these guys here. So if you simplify this now, okay, if you simplify this, you get x to the 3rd, because 6 times 1/2 is x to the 3rd, and that's your answer. Okay, so basically what you're doing, you're dividing that radicand exponent by the index, right? If we try this for a cube root, another example, what is the cube root of a to the 15th? Well, if we write this, or we can write this as a to the 15th raised to some power of 1/3. And from here, you will see that we can multiply. So this becomes a to the fifth. So notice that when it's written in radical form, this number here has to be divisible by the index. That's really what we're doing. Now, what happens if that number is not divisible by the index? And that's where the simplification of radical comes in. Well, if we have an example, okay, simplify. How about if we have the square root of x to the 11th power? Well, 11 is not divisible by the index here, which is a 2. Okay, so notice that the radicand power, okay, notice the radicand power is not divisible by the index, which is 2. Okay? The radicand power is 11 in this case, right? So here we can simplify this. The square root of x to the 11th. Well, what number 2 goes evenly below your power, which is 11? Okay, and we know that that number will be 10. So I could simplify this and say that this is the same as the square root of x to the 10, the square root of x to the 10 times x to the 1. Because remember, x to the 10 times x to the 1 is equal to x to the 10 plus 1, which is equal to x to the 11. Okay? And now, using the property as we did before, we can write this as the square root of x to the 10 times the square root of x. And the square root of x to the 10, because this radicand power is now divisible by this index of 2. So this becomes x to the 10 divided by 2, okay, times the root of x. And 10 divided by 2 becomes x to the 5th root x. Now, this is a step that usually most people skip. So you can skip that step if you choose to. You can skip that step if you choose to. But as always, I suggest that you don't skip steps. Okay? Don't skip steps until you become really good at this. Okay, let's look at another example. Simplify. The cube root of x to the 9th, y to the 14th. So as you can see here, we have more than one radicand power. We have a 9 and we have a 14. 9 is divisible by the index of the radical 3. 14 is not divisible. So what number is divisible by 3 that's just below 14? We don't want to make it a 15 because then we end up at a negative power, okay? So we can say that this is the same as x to the 9th will leave y to the 12th times y to the 2nd power. because 12 plus 2 is 14, right? Y to the 12 times y2 is equal to y to the 12 plus 2, which is equal to y to the 14th. Now, 9 is divisible by 3, 12 is divisible by 3. So we can rewrite this as the cube root of x to the 9th times the cube root of y to the 12th times the cube root of y squared. And the cube root of y to the 9th becomes, x to the 9th is x cubed. Okay, 9 divided by 3. Actually, let me write that out. This becomes x to the 9 over 3 times y to the 12 over 3. And since 2 here is not divisible by 3, we leave that under the radical sign. Okay? So this becomes x cubed y to the 4th, the cube root of y squared. And that's our simplified answer. As always, check if this can be simplified or is divisible by the index 3 in this case. Okay. So you want to make sure you look at this always at the end to see if you can simplify further. Now, how about if we mixed it up now? Example, simplify. How about if I give you the square root of 48 x to the 4th y cubed? Okay. And let's look at the number first. 48 is not a perfect square. There is no number when multiplied by itself give 48. But 48, okay, 48 can be simplified. Okay, 48 can be simplified. So what two numbers, when you multiply them, gives 48? Well, you can go on the side and do some scrap work, okay? We don't use 1 times 48. We have 2 times 24, okay? We have 3 times 48 divided by 3. That will give me 16, okay? So 16 times 3, okay? And if you notice that 16 is a perfect square. So this one here is a perfect square. So we can rewrite this as 3 times 16. Okay, so that will help us with the number. Now, if you look at the radicand power, 4 is divisible by 2. So we leave that as x to the 4th. If we look at the next radicand power, 3. 3 is not divisible by 2. And I keep saying 2 because the index here is a 2, right? So we can rewrite the y cubed is the same as y squared times y1. So we have y squared times y. And notice that I have to extend this line to cover everything. Now, we can rewrite this because look at the things that you know the square root of. I do know the square root of 16. I do know the square root of x to the 4th, and I do know the square root of y squared. Yeah. Those are the things that can come out of there. So if you want, you can only make 2 radicals, which is what I generally do. The 16, the x to the 4th, and the y squared times, and another radical, I leave the 3 and I leave the y. Or you could write them individually, right? Individually mean the square root of 16, the square root of x to the 4th, the square root of y squared, and then the square root of 3, and then the square root of y. I don't recommend that, but you can do that. And you will see that the square root of 16 is 4. The square root of x to the 4th is x squared. The square root of y squared is just y. We don't know the square root of 3. We don't know the square root of y. So putting them together, we have 4x squared y, and these two we just leave back under one radical. Okay. So you just have to find things that the index goes evenly into. Yeah. We just have to look for powers that the index goes evenly into. Let's look at one more example. Example, simplify. How about if we have the cube root of 48 a squared b cubed c to the 4th. So is 48 a perfect cube? Okay. We want to find out, is 48 a perfect cube? Is there a number when you multiply it by itself, do you get 48? And that's what we're looking for. So 48 is not, right? 48 is not a perfect cube, but we can simplify. Let's look at some scrap work in the side, so at least you see what I'm doing. 48. Well, we're looking at a cube root now. So if you notice, okay, 8 times 6 is 48, right? 6 8s are 48. And 8 is a perfect cube. We're looking for cube root. So I can rewrite this as the cube root of 8 times 6. Now, the power here is not divisible by the index. And notice it is smaller than the index. So there is no simplification. Anytime the power is smaller, there is no simplification. It could be exact, but not. So we leave this as a squared. Okay, we look at the next power, b to the 3rd. 3 is divisible by the index 3, so there is no simplification of that. And now if you look at c to the 4th, okay, 4 is not divisible by 3, but I can rewrite that as c to the 3rd times c to the 1. Okay, so if I rewrite my radical now, my cube root, okay, 8 I know is a perfect cube, so I take the 8 out. And the ones that are not, I put them under a different radical. 6 is not. Okay, so we don't know the cube root of 6. We don't know the cube root of a square, so I put that over here. However, b cube can be simplified because the power is divisible by 3. C cube, okay, can be simplified, but c by itself cannot. So now we look at the cube root of 8 is 2. The cube root of b to the 3rd is just b, because b, 3 divided by 3. And then c, 3 divided by 3 is just c. Okay? And on this radical, those nothing in there can be simplified. So we have 6a squared. Make sure the radical covers c. So my final answer is 2bc the cube root of 6a squared c. So just as a hint, right, always look at your final answer. Notice that if any of the power under the radical sign, if any of these powers is bigger or the same as the index, then it can be simplified, okay? Anytime the power of the radicand is equal to or bigger than the index of the radical, then you can simplify further. Okay. In this case, we cannot, so final answer is 2bc, the cube root of 6a squared c. Okay. Now, we haven't looked at any example using, if you recall from the beginning of the video, we have another property here, okay, when we're dividing. So let's look at some examples for when we're dividing. Okay, we only looked at multiplication. So what happens when the radicand is a ratio? Okay, so simplify the root of 3 over 4. Okay. Now, using the property, this can be rewritten as the root of 3 divided by the root of 4. And we don't know the root of 3, so that stays as the root of 3. But notice that 4 is a perfect square, and the square root of 4 is 2. Okay, so you want to recall the square root of 4 is equal to 2. Okay? So you can separate them and simplify, and this will work even when you don't know the radicals. Example, simplify let's look at simplify the square root of 9 halves. So we can rewrite this, okay? So this is the same as the square root of 9 over the square root of 2. And the square root of 9 is equal to 3. So this becomes 3 over the square root of 2. So this cannot be simplified any further, but we do not, okay, leave radicals in the denominator. So what we do, we say we rationalize, we must rationalize the denominator. Okay. And rationalizing the denominator, when it's one term, over here we have one term, okay, let's rewrite it. So we want to rationalize 3 over the square root of 2. So we say rationalize the denominator because we're trying to get rid of the root from the denominator. Okay, we'll try to get rid of the root from the denominator. So when the denominator is one term, in this case it is, right, one term, there is no adding or subtracting anything, we multiply by itself. But if we multiply the bottom by root 2, we must multiply the top by root 2. Realistically, I'm not changing the problem because if you do the division of this, square root of 2 divided by square root of 2 is just 1. Multiplying anything by 1 doesn't change the value. So I'm not changing the value, okay? Now, if you multiply, so let me just put this here in a different color here. So this becomes the square root of 2 times the square root of 2. And this is what the rationalization is we're starting. Now, if you multiply these two things, you will get 3 root 2. But if you multiply the denominator, square root of 2 times square root of 2, you know is the same as square root of 4, or we can say the square root of 2 squared. And we know the square root of 2 squared, right? You have seen that this 2 will cancel out this radical sign just because the root is a 1/2 power. Or you could have done it the first case, the square root of 4, okay? The square root of 4 is 2. So that's divisible by 2, okay? Or we can have 3 root 2 divided by 2. And you always want to check, see if you can simplify when you're finished, because sometimes you will notice that these numbers may be able to reduce. In this case here, they cannot. So my final answer is 3 root 2 over 2. This is our final answer. So we've introduced something new. It's called rationalization, okay? We are rationalizing. And sometimes we just give you a fraction. Sometimes we just give you fractions and we say rationalize the denominator. Yeah. So you will have to know how to rationalize. If I have 4 divided by the square root of 3. So we don't write square root of 3, and it's only one term. So I will multiply this. Let me rewrite that. So we have 4 over the square root of 3. I'm going to multiply this by square root of 3 over square root of 3. If you multiply the top and you multiply the bottom, this becomes 4 root 3 over the square root of 9. Okay, root 3 times root 3 is root 9. And I think I'm going to start writing root 3 squared. And that becomes 4 root 3 over 3. And remember, you always check, can you simplify these numbers? In this case, they cannot be simplified. So this stays as 4 root 3. And let's write the final answer. 4 root 3 over 3. Here is the final result. So we have to get into the habit of simplifying, and we have to get into the habit of rationalizing. Okay, 2 things has to be done. So it's very important that after you simplify, you check to see if you have any roots in the denominator. So let's just make sure that we look at another property, okay, property for radicals. And this one we tend to overlook, right? The square root of a square, okay, is a, but it has to be, because a has to be positive, we said the absolute value of a. Yeah? It's the absolute value, meaning that a can only be a positive number. And that's important because when you use some homework platform systems, right, it's very important that you write the absolute value sign or symbol. Okay? That is very important. So anytime we have an even index ready, this is when that will occur. And I just wanted to point out that property because that one is generally overlooked. But let's look at one more example before we finish. Example. Simplify. And we will look at the square root of 50 x squared y cubed divided by 3z. Okay. So I always check to see before I do anything, is there anything in the bottom here can be simplified, right? Is 50 divisible by 3 and so forth? There's nothing. So the next step is what I rewrite this into 2 radical. This is the same as 50 x squared y cubed divided by the square root of 3z. Now, the square root of 3z in the denominator, right? We don't know the square root of 3. We don't know the square root of z, nor can it be simplified because the power is a 1. And you notice that the index here is a 2. So that denominator cannot be simplified at all. Okay. But the numerator can, because 50, we can rewrite or simplify the numerator. Okay. So here, the denominator cannot be simplified. Yeah. So the denominator cannot be simplified, right? But the numerator can. However, the numerator can be simplified. So if we simplify the numerator, let's move this down a little. Okay. The numerator can be simplified as 25 times 2. Notice that your power here is 2, the index is 2, so that will be simplified. But your power here is 3, so we have to rewrite that as y squared times y to the 1. Okay. As I said, the denominator is not simplified. So if we take out, separate this now into 2, the 25 will be able to, the 2 cannot. X squared will be able to simplify it. Y squared will be, but y to the 1 will not. And all of that divided by the square root of 3z. So everything here can be simplified. So we have 5xy times the square root of 2y divided by the square root of 3z. Now, because these index or powers are 2, okay, we use the property, right? We use this property here. So these letters must have the absolute value sign. And since they both have absolute value, we can combine them to one, the absolute value of xy. We can put them in one absolute value. Square root of 2y over the root of 3z. Now, notice we have a radical in the denominator, so we have to rationalize. Okay, and in order to rationalize this, we'll multiply top and bottom by the root of 3z. So when you multiply these two, that denominator becomes 3z root quantity squared. And the numerator, we have 5, the absolute value of xy. And if you multiply this root times that root, you get the root of 6yz. Okay? Because 2 times 3 is 6. Remember, the radicals, we can multiply them. So finally, we have 5, the absolute value of xy, the root of 6yz, okay? All of that divided by 3z. Okay? And there is no more simplification because nothing can be cancelled. So here is our final answer. As always, I say please practice as many examples as possible because this is how you become better at this. Okay? This is how you become good. And I'll see you in the next video.